Hey guys, in this video we're going to talk about finding points where the electric potential is zero that may or may not be on the x-axis. Now, in a previous video I covered the question of how do we figure out how far this distance is from each of the two charges, where we would call that distance, say, x, and therefore this distance here might be like, say, d minus x, since the total distance between them is d. Okay, and then you could set up an equation with that. It would look like this. Since, after all, the equation for electric potential is V equals KQ over R, and positive charges make positive volts and negative charges make negative volts. Okay, and so when you did go ahead and solve for that distance, which you might call x1, you would churn through the algebra and get this answer. Now, if you need to pause me and go over the algebra for your own benefit, then go ahead and do that. The other point, P2, we also talked about how to find. It's pretty similar. You might call that distance x2, and then your equation might look something like this, where the only really significant difference between the one that I wrote in red and this one that I wrote in blue is this right here, that plus sign. Because after all, while I would still say that the negative q is a distance of some unknown x from the point, the 2q is d plus x away, as opposed to d minus x, right, which was this distance. All right, working out the algebra, you would get this. All right, great, and that's something that we covered in, as I said, a previous video. The point of this video is talking about how do you find the potential at that other point up there, which should really have been labeled P3. There we go. So we're going to talk then about how do I figure out this distance up to that point P3 where the potential is zero. There are in reality a whole lot of points where the potential is zero, right? They're identified by, this dotted red line here. At every single one of those points, the electric potential is zero. And yes, in case you're wondering, I did work that out and draw it to scale. Every single one of those points is a point where the potential is zero. I won't ask you to come up with a graph or a diagram that proves exactly what it is, but I will ask you to figure out this other distance here, which I might call y, because of course it's a vertical distance up. All right, here's what that algebra would look like. Using our favorite equation for potential, KQ over R, we can of course say that the electric potential due to the minus Q is negative, because it's a negative charge, KQ over Y. That's it. It's a distance Y above it, so that would be the potential due to the negative charge alone at that point. All right, now the 2Q over there is going to give me a positive number of volts, because it's a positive charge. And we're going to have 2KQ, because of course its charge is 2Q. It's got twice as much charge. And then over the distance, the distance, what is the distance? That's actually maybe the tricky part of this question, is getting that distance or recognizing what you ought to do to get that distance. Now, if you're looking at that and you're thinking, isn't this, it looks like a right triangle. You are correct, and that means you're about 95% of the way there. You just got to work out that distance. If you think you know what to do, go ahead and pause me and then resume once you think you got it. All right, now if you were thinking Pythagorean theorem, you would be correct. The distance there would be square root of d squared plus y squared. Because after all, d and y are the legs of my triangle, and a squared plus b squared equals c squared. So yeah, the distance would be the square root of d squared plus y squared. And the potential adds up to zero, because that's the whole premise of this question, is that we are finding points where the potential is zero. All right, now, again, pause me, see if you can figure out what to do with the algebra, and then resume once you think you've got it. All right, the next line down in your algebra would look like this. Next thing you'd have to do is, well, we got to get rid of that square root. Or you could cross multiply if you recognize that you have to do that. Yes, you have to cross multiply at some point, but we also have to get rid of that square root, which is of course done by squaring both sides. And now, of course, we could cross multiply. Looking good. Now we just got to group our like terms and solve. And there's my answer, d over the square root of 3. All right, now I should also mention that technically the answer is plus or minus the square root of, or d over the square root of 3. That reflects the fact that there is another y value at which the potential is 0, and that would be directly down below that minus q charge. Okay, because of course this is fairly symmetrical. All right, now this question is really just like a extension of, all right, I got two charges on a line. The other thing I want to address in this video, though, is what if you've got a more complex looking system? Meaning it's not just a line of charges, but there's sort of a two-dimensional layout to them. All right, now this system looks a little more scary. Right, I've got 3 point charges, and only one of them is on the x-axis. So at first blush, this looks like it's going to be a really challenging problem. All right, now, and it might be, the algebra might be, in fact, awful if I was going to really actually do algebra, but it turns out there's a much simpler way to get the answer than algebra. It's going to involve using the graphing function on, say, your calculator or Desmos or something like that. Preferably use your calculator because that's what you're going to be allowed to use on the test. But let me blow this up real quick so that we can nail the geometry here. If I want to figure out the points where the potential might be 0, what I need is actually just a graph of potential as a function of x. And to do that, the first thing I do is I just draw a random point on the positive x-axis. There, I did it. All right, now let me write that down. That is the rule. If you draw a point somewhere else, you're liable to get in trouble. So it needs to be on the positive x-axis. Second, you're going to figure out the distance that each charge is away from that point and write down the total potential equation. Now, as usual, if there's any distance that I'm trying to like solve for or make a graph for, I have to call the distance that this thing is from the origin something. So I'm going to call this distance, oh gosh, I don't know, x. Yeah, all right, we'll call it x. That's a good name. All right, if that distance is x, then the distance that each of the two q's is from it, because I made it symmetrical, is the square root of d squared plus x squared. All right, so far no problems. All right, and then the minus q, it says that the total distance that this one is from the origin is 2d. So that means that the distance it is from my randomly chosen point is 2d minus x. All right, and now I just need to put that into an equation for electric potential. Each of the two kq's is going to give that for the electric potential. Right? Each one is a 2q, so that's why I've got this 2 up here in the numerator. And the distance that each one is away, we said, was d squared plus x squared. So thus, that's the denominator. With that in mind, overall, when I add up the positive charges there, they're going to combine to give me 4kq over that d squared plus x squared. All right, the electric potential from the negative charge is minus, because it's a negative, kq, because its charge is just of a magnitude q, over 2d minus x. Now, in a minute, we're going to try to make a graph of this. If all I wanted to do was like algebra, I could now say, all right, and this whole thing equals 0, and then I've got a lot of algebra ahead of me, but I could solve for that distance x, and it would be a bit of work. But instead, what I'm going to do is throw this into my graphing calculator. There's one important modification, however, that we have to make, and that is this. You need to have an absolute value on the denominator. The reason that you need to have absolute value on the denominator is, all right, it's kq over r. kq over r. R is the distance from the point charge. Distance, if you recall, cannot be negative. It's always positive. Okay, it's always a positive distance. A distance literally can't be negative. Okay, and so that means that you have to do something to make sure that the denominator will always be positive. That's what the absolute values are for. Because after all, if x was big enough, then 2d minus x could be a negative number, and we don't want that. If we want an accurate graph, you have to make sure you put the absolute values on. That is not necessary for the other expression here, and that's because if you take a square root of an expression, especially one where like you squared everything that went into it, it's always going to be a positive number, and we're ignoring imaginary solutions anyway. So you don't have to do anything special with that one, but anytime there's not going to be like a radical or whatever to make sure that you come out with a square root, you got to have those absolute values on there. All right, and now that goes into your calculator. Wait a minute, Mr. Errico. How do I deal with the like the k, q, and the d? Like this is just a symbolic problem. I don't know what k, q, and d are. Have no fear. In order to make our graphs, because after all I really want to know is find a point where the electric field is zero. Find a point where the potential equals zero, right? I don't really care about the value of k and q. I just want to know what x is. I'm going to make the following substitutions. Substitution number 1. KQ is 1. Might not be true, but it's going to make it possible to make my graph work. Second substitution. D is also 1. And 1 squared, of course, is 1. And 2 times 1 is 1. All right, so let me write those down. And that's going to give me this simplified equation that we can graph. All right, you can throw that into the graphing function on your calculator, and if your window size is appropriate, it should spit out some kind of a graph like this. Whoa, that's a pretty cool looking graph. All right, now Desmos will conveniently solve for like, you know, all the interesting points. Like it found all the minima and the maxima and the roots. Now, what you need to understand are what each of those points is telling you. Because, yay, you made a graph, but, like, what do the answers mean? Like, what are all these things? Let's begin with, this is a graph where the vertical axis is electric potential, and the horizontal axis is position. Okay, now, the first question that was asked was, where does the electric potential equal 0? All right, well, on the graph, that's these 2 points. But what does that mean? All right, well, let's take a look back at the diagram that I drew. The point x equals 1.541. Well, let's see, that right there is 1.541 d. And d, if you recall, is like a specific distance on our graph. And the distance 2d along the x-axis is where the minus q was, which, by the way, notice there's x equals 2. Oh, how far down does this go? Down to negative infinity, because that our path along the x-axis would pass straight through the minus q. And so when you reach x equals 2, you are at negative infinity volts, which obviously that's a little bit impossible, but whatever, that's not the point. I'm just trying to orient you. X equals 2 is exactly on the minus q. So x equals 1.541 is, well, let's see, x equals 1d would be there. 1.5d would be about there. So like hereabouts is that point, right? This point is located right there. That's where we're saying the potential is 0. But there's another one, 2.726. All right, so almost 3D, or like 2 3/4. 2D was, again, here. 3D would be like, I don't know, hereabouts. I'm in the middle of my words. So something like maybe right in the middle of the letter F there is this other point where the potential is 0. Now, these other 2 points, let me pick a different color. Those other 2 points are local maxima in this case. There's no local minimum around. A local maximum or minimum is a point where the rate of change in the volts is 0. And there was a fact that we wrote down early on in the unit, which is that the electric field is, in fact, the rate of change in the potential. So like a strong electric field corresponds to the potential changing very quickly. A weak electric field means the potential is not changing very quickly. All right, but importantly, if the slope, which is a rate of change, which is a derivative, all right, of your graph is 0, that's a local maximum or minimum. In other words, this point, negative 0.059, which is like right there, like barely past the origin on the negative side, at that point, the electric field is 0. So that local maximum on my graph is telling me a point where the electric field is in fact 0. All right, and then there is apparently one other point, 4.178, which would be like, I don't know, way like here or something, right? At that point, also the electric field is 0. Now, if you're trying to understand why it would be 0 at that point, we're not going to go through the vector addition because it's actually impossible to solve for those points algebraically. But we could draw a diagram that would at least help you to understand how it could be 0 at those points. The 2q up here, this one, would be making a field that goes like, nearly vertically downward, but not quite. The other 2q would be making a field that goes like that. So if I add up their x components, it might give me, say, this altogether. The electric field due to the minus q, because it's a negative charge, would go towards it. But it's pretty far away, so the field it produces might not be especially powerful. But if it is exactly equal in magnitude to the total field from the positive charges, this one, then the two fields together would give me exactly 0. So at that point, the electric field is 0. What I'm telling you is the graph tool is amazing. It can tell you all this stuff just by being able to write out the geometry formulas for how far away each of those points are. You can find the points where the potential is 0. You could make a graph to find out actually what all of the potentials are equal to. If we hadn't canceled out the k, q, and the d, that might have worked. Okay, but also you can find out points where the electric field is 0, even in situations where it would be algebraically impossible or at least very difficult to do so. All right, well, that concludes this lesson. I hope you can find some application to this and homework 2, and also to the later homeworks and the lab that we're going to do in this unit. So hope you paid attention, took good notes. See you in class.